Hi, I'm Bill Leinhart. I'm currently at the Isaac Newton Institute running a program rich on nonlinear tomography. Well, I did some simple MATLAB script demos on one-dimensional inverse problems and some of the basics of inverse problems. A lot of people asked how to do that in Python, and so I accepted the challenge. In particular, we have the CIL, the CIL library for doing, well, mainly tomographic reconstruction, image reconstruction, inverse problems. And since that has a Python interface, I thought it would be nice to illustrate some simple 1D examples in Python and show how you would also solve them using the functions available in CIL. Actually, I'm not that experienced in Python, so this is from the perspective of somebody who knows MATLAB, trying to transfer that knowledge to Python. Okay, so let's go to share screen. Okay, so I've started a Jupyter notebook. Maybe okay, so there was some little bit of an overhead in making sure that you had the right libraries installed for Python. So actually, this is a Linux computer, and I use Micromamba to create an environment in which I had the CIL installed. And there's many ways to do that. And I started the Jupyter notebook, and now I'm running within my Firefox browser. So that's the context. Of course, you can just type the Python at the command line or whatever you want, put it in an editor and run it. Okay, so we did this at the hackathon for the CIL library, and here's a link to the hackathon. I'll put a link to this Jupyter notebook in the commentary for the video. But this was a hackathon as part of our R&T program, and the link to it's there, and also the link to the CIL. If you want to see the right web page, it's that one, the core imaging library of the Collaborative Computation Project in Imaging. Okay, so some prerequisites. I'm importing Numpy, which has many of the MATLAB-like functions in Python, and I'm calling it NP just to save typing. The MATLAB style plot library, plotlib, as blut, and I need some components of CIL that I'm just going to load those. I need I'm going to import the CGLS, conjugate gradient least squares, and also matrix operator, and so on. I wrote a script called deriv2 that we'll look at in a moment maybe, but it's more or less the same as deriv2 in Per Christian Hansen's regularization toolbox. I'll tell you what the difference is when we look at it. But the point is, it's the operator, the integral operator on an interval 0, 1 that basically integrates twice. So its inverses differentiate twice. But of course, you have to decide which boundary conditions you put in. But the point is, inverting it, which is roughly differentiate twice, if you differentiate noisy data, you're taking differences of nearby values, and so it typically blows up. On the other hand, it's only mildly ill-posed, and if you want a way of thinking about this, if you used a Fourier basis of trigonometric polynomials, then differentiating is just multiplying by frequency. So multiplying by frequency squared. That's mildly ill-posed, but it's still ill-posed. Okay, so just like in the regularization tools, deriv2 gives me a matrix A, a right-hand side B, and an example solution X, which in my case, it's actually just AX equals B, rather than having a different formula for it. And deriv have several examples, hence the number 1. So if we plot the X that it's given, it's very, very simple. It's just a straight line. And so that's what we're trying to recover from knowledge of its integral, double integral. You have to get a little bit used to the syntax if you're used to MATLAB. So I've A, B, and X all come out of deriv2. They're actually NumPy arrays, so matrices and vectors. So when I do A at X, that actually does matrix multiplication, so star in MATLAB. And I want the norm of that to see how well my X fits. So I'm going to use a NumPy linear algebra function norm. So I've referenced it like this. And it's 0 because it fits exactly in my version of deriv2. Okay, so we don't want it to fit because we're not inverse criminals. And so we get the B vector and we add some noise. And in MATLAB, you use maybe rand_n for normally distributed noise. And here it's np.random.rand_n. And I've scaled it by some factor. And so this is, this will be unit variance mean 0, Gaussian, pseudo-Gaussian vector. So you know, scale the variance, and if you plot it, you see it's introduced quite a lot of wiggliness into the nice smooth function. So the point is, B here is a function whose second derivative is a straight line. So surprisingly, looks like a quadratic, right? And now we've messed up, and differentiating it would go horribly wrong if we did it numerically. Well, how bad is this problem? In MATLAB, we just use SVD to have a look at the singular values and maybe plot them on a log or linear scale. It's easy enough to do that in Python. There's always a few little irritations that you have to learn to get used to doing it in Python if you're used to MATLAB, but possibly just looking up the help. And okay, so np.linl.svd is the singular value decomposition of these, I suppose it's a full rather than sparse matrix. And it gives me a U, S, and a V. Just be a little bit careful as to which way around these are stored. And the S, I think, is actually, this is a vector rather than if you did that in MATLAB, it would give you a diagonal matrix. Okay, so let's plot these singular values. There they are. Oh, by the way, to execute code in this notebook, just like the MATLAB notebooks, we do Shift Enter. Oh, I haven't executed the others yet, so okay, go back, Shift Enter that one. Right, let's plot it there. It's worked out that one. Let's replotted that one. Of course, it's slightly different because it's sampled from a number generator. and now it works. And I don't know why this is. Why I can't see the whole of the plot. Okay, I guess I've got the scroll bar. Okay, so this is plot of the singular values, and you can see they're going down. Well, it looks like some power, and so yeah, that's why I have to scroll because I've done several plots in the same window. So on a log scale, you see it's kind of more or less straight, indicating roughly a negative power law. And then there's this disastrous kind of jump down, which suggests to me that there's one-dimensional null space. And so maybe it's down to the implementation. So perhaps you'd like to look at that and see what that null space is. So you could plot the, say, the last singular vector and see what it is exactly that we can't find. But I think it will be revealed later on in this case. So it's mildly opposed, but it does have a definite null space. So it's going to be hard enough to do. Let's try Tikhonov regularization. I'm going to use the block formulation of Tikhonov. In NumPy, we can use stack, vstack, stack vertically. In MATLAB, we just put matrices as though they were rows of a matrix, and it would stack them vertically. And what I've stacked is A and 0.01 times EYE, just like in MATLAB, that's the n by n identity matrix. So I've stacked A with antimatrix times a factor, and the right-hand side I just stacked with some zeros to match it. So it's like I've got the equations x equals b, and I've also got the equations 0.01 x equals 0, and since I'm doing the least squares, that tries to make the norm of the x small. Okay, so I would normally just use backslash now to solve it in MATLAB. There's a variety of options. For some reason I use this least squares solver. But the point is, it's now a well-conditioned matrix with respect to inversion, I hope. Well, I've regularized it, so it should be. Here's the thing, make sure that my regularization actually does determine that element in the one-dimensional null space. So that's the thing to think about. Anyway, a Tikhonov regularized solution looks surprisingly good at this end and really rather bad at that end. You can play with the Tikhonov factor, and you can also use different matrices other than the identity if you want. Okay, so you can now play the same kind of tricks that we did in MATLAB once you mastered the Python versions of things, in particular NumPy and the plotlib. I'm just going to show you how to do it in CIL, because although CIL's designed to do multi-dimensional imaging problems, it's probably nice to practice on 1D examples because they're really quick and you can easily see what's going on, and then you can go on to doing tomography, for example. So we need to do some CIL-specific thing. I've got a matrix A, which is a NumPy array, and I need to make a matrix operator in the CIL framework. And I suppose the point is that this matrix operator has a method to do the forward A times X and the adjoint A adjoint times X. And normally in big tomography problems, that would be implemented without storing the entire matrix. In other words, you'd work them out on the fly, for example, by intersecting lines with voxels, something like that. But actually, this matrix operator, all it does is store the matrix and multiply it. And then I've got to make a vector data out of Bn, which was, of course, the thing with the noise. So I'd better execute that. I suppose I put that in there so that you can actually do help on matrix operator. But of course, you can look at the documentation for the CIL on the CIL website as well. I guess I'd already done that. It's gone up. Okay, so the call CGLS, conjugate gradient least squares. So this actually does solve the least squares problem, but of course with an ill-posed operator, that you'd expect that would go a bit wrong because it would try and overfit it. But in this case, I've only asked it to do 4 iterations. And so there are the iterations, and the objective function decreases very, very quickly at first, 10 to the minus 3 to 10 to the minus 5. And then it's not really decreasing that much. And that's the point, that it's, because it's ill-posed, you don't want to overfit it. And okay, so with that 5 iterations, the solution here is a bit wiggly. I guess we don't expect to get that because it's got some null space, but it's not really as smooth, but I didn't do that many iterations. What happens if we do least squares with the noisy data? Well, we get nonsense. So also, if we iterated the CGLS for enough iterations, we'd also get nonsense. Okay, so now we're going to do CGLS on this block matrix with the identities that shows that you can do Tikhonov, or if you want generalized Tikhonov or whatever. So in this case, our L matrix to define a generalized Tikhonov is going to be the identity operator. And this is an identity operator within the CIL framework of operators. We've also need a domain geometry, and normally this would describe your setup of pixelated grids for a tomography problem and so on, but it's just necessary to define one for this. So we've got the same alpha, and then I use block operator of the A and alpha times L. So that's a block operator, and of course CIL knows to multiply that by a vector, you use the 2 blocks and you get a block vector as the output. And so we have to augment the B as a block vector, and here's just setting it to zeros on the range of L. And okay, so that makes the vector of B's with the zeros added to it. Just check whether they, if you remember, the BOP was the B operator, and we used the noisy data to make it, right? So now we can do CGLS with Tikhonov by applying this to the block operator. So, I mean, obviously, you might want to stop after you'd fit to a certain amount. One thing now is that this matrix is relatively well conditioned because it's augmented by the Tikhonov, and CGLS converges faster for better conditioned matrices. So it's made a huge amount of progress in one step. Okay, so let's see how the Tikhonov solution's gone. Obviously, you have to play with how much regularization you need for how much noise. and it was quite noisy data. And here's our CGLS Tikhonov reconstructed solution compared to the genuine solution. Okay, so that's a very quick NumPy version of the Deriv2 example from Reg Tools, and how to use block CGLS to solve the Tikhonov problem using the CIL library. And the point about CGLS is that it will work for very large sparse matrices where you don't store the whole matrix, but you calculate the matrix times a vector and the adjoint of the matrix times a vector on the fly as you go. Okay, thanks for listening, and let me know in the comments if you'd like more like this, whether we should do more examples. As for CIL, there are lots of tutorials on the CIL website, so maybe this has given you a taste for it. If you've got a tomography problem to do, that might be the right way to go.